This is Algebra 2, Unit 7, Lesson 4, on horizontal stretching of functions. The horizontal stretch in compression is probably one of the hardest ones, but it's very important, especially when you're modeling a process over time and shrink the time interval. So let's explore this, starting out with an absolute value function. So we have the absolute value function f of x equals x minus 2 minus 3. So using your calculator, sketch a graph of f on the axes provided. Label the coordinates of its vertex point without using your calculator. Well, we're going to use the calculator, so let's figure it out. So first of all, I'm going to set my window on my graph. So if I grab my calculator here, my window is for the x values will be from -3 to 10. -3 to 10. My y values will be from -5 to 8. X is -5 for the minimum, 8 for the maximum. All right, now when I go to y equals, I want to do the absolute value of x minus 2, so alpha window key. Absolute value, see the bars here, is number 1. X minus 2, and then minus 3. So, based on this graph, when I graph this, here is my graph. And you can see it goes through to the vertex here is at 2, -3. And that should be noticeable here when we do this right here, because the vertex comes from here and here. Remember when we did the parabolas, it was inside was the opposite sign and the outside is the same sign. So if we do absolute value of x minus 2 minus 3 and we draw it in, I'll even do it in blue so that you can, it looks like what's on the calculator. It came down like this, about there or so, and then came up like this. It's a V-shaped graph. So this is f of x equals x absolute value of x minus 2 minus 3. And the vertex for this one will be at 2, -3. 2, -3, because it came from here. 2, -3. Okay, now let's do the function g of x equals f of 2x. Determine a formula for g and then graph it on the axes. Okay, so this says g of x is equal to f of 2x. So if we take the f of x function and plug in 2x, we can get g of x. So g of x is going to equal the absolute value. We plug in 2x minus 2 minus 3. All right, so if I graph that on my calculator, I'm going to go down to the red one here. It's going to be absolute value of 2x minus 2 and then minus 3. Let's see what happens to this function. All right, so what happened to that function? Well, it got narrowed and kind of squeezed together. And your vertex moved, so it moved from here to here. So if we put that on our sketch, here's our sketch. I'll do it in red so it looks like what's on the calculator. It's going to narrow, and it's going to go kind of like this, and then up like this. A little crooked, but you get the idea. Okay, so it's going to be a narrower function. So this is going to be g of x. I'll do it in red. G of x is equal to the absolute value of 2x minus 2 minus 3. And your vertex right there is going to be at -1, or 1, -3, I'm sorry, I wrote that wrong. 1, -3. So that's right here, 1, -3. Okay, now let's do the h function. H of x equals f of 1/2 x. Determine a formula for h and graph it on the axes, and then find the minimum point and label on the graph. Okay, so if I take h of x, I'll do this one in black here. H of x is equal to f of 1/2 x. So we take this function, and for x, we plug in 1/2. So it's 1/2 x minus 2 minus 3. Let's see what happens on this. All right, so I'll go down here, absolute value of 1/2 x minus 2 and then minus 3 and graph it. Okay, what happened to that function? Well, it widened out, it flattened out, and the vertex is now at 1, 2, 3, 4, 1, 2, 3, 4, negative 3. So if I do a sketch like that, let me look at my, all right, so here we go. I'll do it in black so it looks like what's on the calculator. It was a wider function, it went down like this, and then came up like this, kind of like that. Okay, and our vertex right there was at 4, negative 3. Okay, so if we summarize your finding for each function, we found on this the turning point for f of x, which was the blue function, was at 2, negative 3. F of 2x was the red function, this one over here, was at 1, negative 3. And of f of 1/2 x, which was the black function, that was at 4, negative 3. So what stayed constant about the turning points? There's the 3 turning points, the y value. The y coordinate stays the same. Okay, but here's what the important part is with the horizontal stretch. What changed and how did it change? Well, we started out with f of x, the blue function, and then we went f of 2x, did the red function. What happened to that? All right, well, this started out as x coordinate was 2, this is going to be 1. So the y coordinate stayed the same, but for f of 2x, what happened? The x coordinate was divided by 2. Divided by 2. Okay, and what happened with f of 1/2 x? The y coordinate stayed the same of all of them, but what happened to this? Started here, it ended up at 2, and this one ended up at 4. The x coordinate was multiplied by 2. So that seems kind of counterintuitive. Okay, so when we had 2x, it's basically you took half of what you did. And when it was 1/2, you multiplied it by 2 instead. So it's counterintuitive except for about horizontal dilations. So when you are doing by a whole number here, if k of x represents a horizontal, if k is greater than 1, it's going to be a horizontal compression by a factor of k. So you're going to squeeze something together closer like this. All right? And then 1 over k of x represents a horizontal stretch of x. So you are grabbing it by the sides and widening it out. So this one will narrow, but this one will widen. So if the k value is greater than 1, it's going to narrow the graph up. If the k value is less than 1, it's going to stretch it out and widen it up. So you can see each one of these, it seems kind of counterintuitive when you're doing these. Now let's try the quadratic function. F of x equals x squared minus 12x plus 20. So determine the coordinates of its turning point by using the equation of the axis of symmetry of x equals negative b over 2a. Okay, so the x coordinate, x equals negative b. Remember, a is going to be 1, b is going to be negative 12, c is going to be 20. So negative b would be positive 12. Over 2 times a would be 2 times 1. 12 over 2 is 6. So the x coordinate is going to be 6. And then to find the y coordinate, f of 6 is equal to 6 squared minus 12 times 6 plus 20, which is 36 minus 72 plus 20, which is negative 16. So the vertex is going to be at 6, negative 16 for this quadratic function. So now, if g is defined by g of x equals f of 3x, what should be the coordinates of a turning point based on our previous work? Okay, now what we just did, remember, is if it's f of 3x, is this going to be a horizontal compression or a horizontal stretch? Well, if it's 3x, it's going to be a horizontal compression. So what are we going to do with the coordinates? Well, what happens to the coordinates? We're starting with 6, negative 16. And we said the y-coordinate is going to stay the same. The x-coordinate is going to be multiplied by what? So we have to multiply the x by, what is the compression factor? Well, if it's 3 here, that means we have to multiply by a third. So it's going to be 6 times a third, negative 16. 6 times a third is going to be 2, negative 16. So since this is a whole number, it's going to be a compression, we are multiplying it by a factor of 1/3. So g of x, this chord, the vertex, will be at 2, negative 16. Now, determine a formula for g of x, and then use the turning point formula to verify your answer from part B. Let's make sure we're right. Well, remember that g of x is equal to f of 3x. So that means we take 3x and plug it into the formula. So 3x, quantity squared, minus 12 times 3x, plus 20. Now be very careful. What's 3x quantity squared? 3x quantity squared is 3x times 3x, which is 9x squared. 12 times 3 is 36x, minus 36x, plus 20. So our turning point is x equals negative b over 2a. Negative b would be positive 36 over 2 times 9 is 36 over 18, which is 2. So 2 matches. And then for y, g of 2 will equal 9 times 2 squared minus 36 times 2 plus 20. 9 times 2 squared is 4 is 36, minus 72 is negative 36 plus 20 is also equal to negative 16. So this still gets to negative 16. So there we go. So we use the formula here. This would be g of x. It would be a horizontal compression. It would be narrower than the original. Now, show that the y-intercept of both f of x and g of x are equal. Why does this make sense from a horizontal dilation perspective? All right, now, the y-intercept, what do we know about the coordinates of the y-intercept? At the y-intercept, the x-coordinate is equal to what? It equals 0. Okay, so if we take f of 0, or g of 0, f of 0, sorry, and plug it in, we get 0 squared minus 12 times 0 plus 20 will equal 20. So the y-intercept is going to be 20. Same thing with g of 0. It's going to be 9x squared, so it's going to be 9 times 0 squared minus 36 times 0 plus 20. Because x is equal to 0, the y-intercept will always be the same. So your y-intercept does not change because x equals 0 at the y-intercept. All right, now for the last one, we can truly investigate why this is happening by looking at a function that is only represented graphically. So let's save this problem for class the next day, and we'll go over what happens graphically when we deal with this problem.